All right, the first thing we ask ourselves when we have two different objects, like in this case, if we have two matrices, is when are they equal? So we say that two matrices are equal, so A and B are equal, and of course the notation is A equal to B using the equality sign, when the following two conditions are satisfied. Well, first, A and B must have the same number of rows and the same number of columns. So they have to have the same dimension in order to be equal. If they don't have the same dimension, they are not equal. And then when they have the same number of rows and the same number of columns, then they're going to be equal if they're entries in their respective position. Aij is equal to Bij for all I between 1 and m, so that's the number of rows, and for all j between 1 and n, where n is the number of columns. So same size, all the entries are equal in their respective position. So very, very similar definition that we had for two vectors in our n. So here's an example. Find the values or the value of x such that first we'll try when is a equal to b, and then we'll check if we can find a value of x such that a is equal to c. So for the first question, if we're trying to check if a is equal to b, well, the first thing to notice is that a and b are they're two square matrices, and their size are 2 rows, 2 columns, so our two matrices in M 2 by 2. So there's hope for them to be equal if you set them equal to each other. So if you write A first, so we have 2, 1, 3, and x, and we want this to be equal to B, where B is 2, 1, 3, and 5. Well, here we can see that they have the same size. The first entry in the first column of A, let me just write the letters for both of them under. So remember, this is A, this is B. So if you look at the first entry, first row, first column, which is 2, it's matching the 2 in the first column, first entry for B. First row, second column, we have a 1, which is equal to 1. And then second row, first column, we have a 3, which is equal to 3. So the only thing that we don't have is second row, second column, we have x equal to 5. So of course, these two matrices are going to be equal if and only if. So this is only going to be happening if and only if x is equal to 5. So when x is equal to 5, these two matrices are equal. So for the other question, so we want to know if A is equal to B. So A is equal to C, 1, 2, 3x. And we want to know when is this equal to C, which is 2, 1, 0, 3, 4, 0. So here we have A and we have C. And even if it feels similar, like you see here, just like the previous question, my 2 is equal to 2, 1 equal to 1, 3 equal to 3, and it feels like, maybe that x could be equal to 4, but the problem is this extra column. So here these zeros, even if it feels like they're redundant, these two matrices are not the same size, so they cannot be equal. So here they cannot be equal because A is a 2 by 2 matrix and B is a 2 by 3 matrix. So not the same size, they cannot be equal whatsoever. Okay, so it's sad, but that's it. Not same size, but not equal. So the next operation, so we want to define matrix addition and subtraction. So here it's very, very similar than what we did with vectors. You can add or subtract matrices as long as they have the same size, and then as soon as they have the same size, you just add or subtract the corresponding entries. So first thing you have to check is that A and B are two matrices of the same size. Then you can compute the sum AB just by adding the entries together. So you can also compute the difference between A and B just by subtracting the entries. And if these matrices have different size, so if they have different size, then we simply say that these operations are undefined. Okay, so in matrix notation, you can simply say that the matrix A plus B, the entries are simply, so the element on the ith row, jth column of the sum is Aij plus Bij, and then the entry of the difference, A minus B, on the ith row, jth column is simply Aij minus Bij. So let's go and look at an example. So here's an example. So we have three matrices, matrix A, B, and C. The first thing you should probably do before you do any operation is just look at the dimension of the objects you're working with. So for example, A, there's 3 rows, 4 columns. So A is an example of a 3 by 4 matrix. Same thing for B. B has also 3 rows and 4 columns. So B is also a 3 by 4 matrix. But the matrix C here, square matrix, 2 rows, 2 columns, so it's an example of a 2 by 2 matrix. So if you want first to compute A plus B, well, A plus B will be defined because these two matrices, A and B, they have the same size. Like meanwhile, that matrix C has a different size, so because that matrix has a different size, it won't fit if you're trying to add A or B to it. So A plus B, so because they have the same size, the only thing you have to do is add the entries. So here we have I'll write down all the details. Normally when you're adding two matrices, just like if you're adding two vectors, you can just write the operation, but just for the sake of completeness, I'll do it. So here, 2 plus, so we have 2 plus minus 4. That will be first entry, first row, first column. So then we have 1 plus 3. Then we have 0 plus 5. Then we have 3 plus 1. That's for my first row. Then minus 1 plus 2. Then 0 plus 2. You just have to be careful. So 2 plus 0. And 4 plus minus 1. And then 4 plus 3. Minus 2 plus 2. 7 plus minus 4, and finally 0 plus 5. Then if you just do the computation, so if you do first entry, first row, first column, so 2 plus minus 4, that's minus 2, 1 plus 3, that's 4, 0 plus 5, that's 5, 3 plus 1, that's a 4, then minus 2 plus 2, that's 1. 0 plus 2, that's 2. 2 plus 0, that's also 2. 4 plus minus 1, that's 3. 4 plus 3, that's a 7. Minus 2 plus 2, that's a 0. 4 plus minus 7 plus minus 4, that's 3. And 0 plus 5, that's 5. So that's your sum. Now if you want to subtract A and B, again, these will be defined because they have the same size. So A minus B. So again, here I'm writing all the detail. Normally, you just subtract right away, but just for the sake of completeness, for that example, I'll do a long road there. So 2 minus 4, 1 minus 3, 0 minus 5, 3 minus 1. Then you have minus 1 minus 2, 0 minus 2, 2 minus 0. 4 minus 1, 4 minus 3, minus 2, 7 minus 4, and 0 minus 5. So if you do the subtraction, you get 6 minus 2 minus 5, 3 minus 1, that's 2. We have minus 1 minus 2, that's minus 3. 0 minus 2, that's minus 2. 2 minus 0, that's 2. 4 minus minus 1, that's 5. 4 minus 3, that's 1. Minus 2 minus 2, that's minus 4. 7 minus minus 4, so that's plus 4. So you get 11, and 0 minus 5, that's minus 5. And for all the other operations, so for a plus c, or b plus c, or a minus c, or b minus c, because these matrices they don't have the same size between a and c, and b and c, these are undefined. Okay, normally you say why, okay, not the same size. You can specify why they're undefined, just because either the number of rows or columns or both are not the same. So all these operations here, a plus c, b plus c, a minus c, b minus c, undefined. But meanwhile, a plus b and b minus a, we were able to compute them because they have the same size. So that's it for addition or subtraction. Next operation is scalar multiplication. So again, scalar multiplication is another operation that is very similar to what we've done in with vectors. So the definition here for scalar multiplication is if you start with a matrix and a number, then the scalar multiplication of k with a, basically what you do is you take every single entries of a and you multiply it by the number k. It's always defined, and it doesn't change the size of the matrix. So if you look at matrix notation where A is the matrix with the entries aij, if you multiply A by k, then every entries inside the matrix A is multiplied by k. Now let's look at some examples. So next example, so for the following matrices, let's multiply A by 2, let's multiply B by minus 1, and let's multiply C by 1/3. So for the first one, so 2 times A, again here I'm doing all the detail. Normally you can write the answer, that would be okay for a full solution. So 2 times 2, 3, 4, 1, 3, 1. So let's use some color here, might as well. So let's say 2 is going to be in orange. So if you multiply by 2 throughout, you're going to get the following matrix. So you're going to get 2 times 2, 2 times 1. So 2 times 2, 2 times 1. Then you're going to get, so if I'm just rewriting my matrix here quick, so 3, 3, 4, 1. So you're multiplying by 2 everywhere. So what you're going to get at the end is the matrix 4, 2, 6, 6, 8, and 1. So every entries of A were multiplied by, sorry, so mistake there. You won't see that. 2, okay, sorry. So 4, 6, 8, 2, 6, 2. Every entries were multiplied by 2. Next example, let's multiply B by minus 1. So let's write down B quickly. So 0, 2, 7, minus 1, 3, minus 5. So we're multiplying by minus 1. So if minus 1 goes in, again here I'm going to write all the detail. If you write the answer right away, it's going to be accepted as a complete solution unless it's specified. So here, so if I write the entries quick, so 0, minus 1, 2, 3, 7, and minus 5. So you're multiplying everywhere by minus 1. Of course, you could simply just change all the sign of the entries, that would work as well. So so if you multiply, you're going to get 0, minus 2, minus 7, plus 1, minus 3, and plus 5. So all the signs inside the matrix B were changed. So 0, minus 2, minus 7, 1, minus 3, plus 5. Last example. So let's multiply C by 1/3. So 1/3 C. So here C is 9 minus 6, 3, 3, 0, 12. And you're multiplying everything by 1/3. Another way to say this is that you're dividing every entry by 3. But it's completely equivalent. So here, let me just rewrite things quickly. So 9, 3, minus 6, 0, 3, and 12. And then every single entry is multiplied by 1/3. Again, you're just doing it. You don't need to write as much details unless I specify it. So if you divide by 3, you're going to get 3 minus 2, 1, and then 1, 0, and 4. So scalar multiplication is just like what we did with vectors. You just multiply every single entry by the scalar. And that's it. Now let's look at an example that combines addition and scalar multiplication. Let's compute the matrix C, which is A plus 2 times B. So A plus 2 times B. So if you write A first, you have 1, minus 1, 3, 1, minus 4, 5, minus 7, 2, 3, 6, 9, 3, plus 2 times 2, 2, 2, minus 1, minus 3, 1, minus 5, 2, 2, minus 4, 5, minus 2. So the first thing I'm going to do is distribute D2 inside my matrix. So just by multiplying every single entry of B by 2. So just have to be careful here. So I'm rewriting A here. If I can just copy this. So A is not changing. Okay, and then if you multiply by 2, you're going to get plus. So you multiply every entry by 2, 4, 4, 4, minus 2, minus 6, 2, minus 10, 4, 4, minus 8, 10, and minus 4. And then you just need to add everything up. So if you add, you're going to get 1 plus 4, which is 5, minus 1 plus 4. Minus 1 plus 4, you get 3. 3 plus 4, you get 7. 1 plus minus 2, you get minus 1. Minus 4, minus 6, that's a minus 10. 5 plus 2, that's a 7. Minus 7, minus 10, that's minus 17. 2 plus 4, that's a 6. 3 plus 4, that's a 7. 6 minus 8, that's a minus 2. And 9 plus 10 is 19. 3 plus minus 4, that's minus 1. So just be careful. Again, very, very similar to what we did with vectors. So scalar multiply B by 2, add up the two things. And that's it.